Hello, I would like to present an ethical, adaptive method for assessing information reliability under uncertainty for 5G and Internet of Things systems. The development and use of fifth generation 5G mobile networks has given a rapid impetus to the further development in various fields. It is increase in the data transmission speed and the increase in network capacity that open up new prospects for their use in industry and the corporate segment. From the feature, you can see that 5G has significant advantages over 4G, namely increase by 10 times the average speed of user data transfer, increase in user mobility by 42%, increase in peak data transfer rate by 20 times, reducing signal delays by 10 times, increase in the density of devices by 10 times per square kilometer. The development of fifth generation 5G mobile networks has become an important factor in the development of Internet of Things. A significant increase in the number of devices in application with Internet of Things technology requires extensive opportunities for fast data transmission, low signal delay, security and reliability in data transmission. Most of these criteria are addressing by 5G. Also, an important aspect for the use of 5G in the Internet of Things is the technology of dividing the radio network into separate layers, which allows you to divide different types of devices into segments and that do not intersect with each other and thus provide them with distributed access. This is important when implementing smart home, smart city, or when used in industrial Internet of Things. The development of Internet of Things in turn gives a powerful impetus to the rapid implementation of Industry 4.0 as well as digital twins. Um, the purpose of the article is to develop an adaptive method for assessing the reliability of information under conditions of uncertainty. First, the use of a priori and posteriori information of the decoder. The method makes it possible to adapt to changing the parameters of encoder and decoder of turbocode and LDPC code by using the logarithmic ratios of likelihood functions and the calculating values of noise dispersion. LDPC codes introduced into the 5G standard for further replace convolutional codes and turbo codes. They are used to support high throughput, coding rate variation, hybrid automatic retransmission request, and have good error correction capability. You can see the LDPC encoding scheme, which includes transport block, CRC attachment, LDPC base graph selection, code block segmentation and code block CRC attachment, LDPC encoding rate matching and cloud concatenation. The LDPC decoding scheme is the reverse process of LDPC encoding chain. You can see structural diagram of a modified iteration turbocode decoder. Modified decoder consists of two decoders, two interleavers, two deinterleavers, and a module for calculating the normalized number of changes in the sign of a posteriori a priori logarithmic of the likelihood ratio. This slide presents the basic formulas for calculating the logarithmic ratio of likelihood functions and calculation of the normalized value of uncertainty index. The output logarithmic ratio of likelihood functions of the decoder is equal to the sum of the channel a priori and external logarithmic ratio of the likelihood function. The total uncertainty index is determined by the sum of uncertainty indexes for all decoding iterations. Simulation results. Analysis of the simulation results shown in the figures show shown that as the data block size increased from 400 to 1000, the decoding uncertainty index curve approaches the decoding error probability curve. For example, for data block size equals 1000, 8 decoding iteration with a signal noise ratio of 1.4 decibel, the value of the decoding error probability is 5 multiplied by 10 to the minus 5 power, and the value of the decoding uncertainty index is 9 multiplied by 10 to the minus 5 power. For the data block size equals 1000, for decoding iterations with a signal to noise ratio of 1.4 decibels, the value of the decoding error probability is 1.5 multiplied by 10 to the minus 4 power, and the value of the decoding uncertainty index is 2.5 multiplied by 10 to the minus 3 power. The analysis shows that with an increase in decoding iteration, the accuracy of assessing the reliability of information increase. So for 8 decoding iterations, the values of the correlation coefficient change for 90 to 98%. For 4 iterations from 80 to 92%. For 2 decoding iteration from 60 to 80%. Conclusion. The article proposed an adaptive method for assessing the reliability of information under condition of uncertainty throws the use a priori and a posteriori information of the decoder. The method allows you adapt to changing the parameters of the encoder and decoder of turbocode or LDPC code through the use of likelihood ratio and the calculated values of the noise dispersion. In contrast to the known results, due to the use of the scene change a priori and a posteriori logarithm of likelihood ratio during iterative decoding and taking into account the noise dispersion values in the channel reliability parameter. The method allows obtaining information reliability values without using an additional service channel. Simulation analysis shows that with an increase in decoding iteration and the size of data block, the accuracy of the information reliability estimate calculated by the decoder without reducing the throughput approaches the reliability estimate when using an additional service channel. So for data block equals 1000 8 decoding iteration with a signal to noise ratio of 1.4 decibel, the value of the decoding error probability is 5 multiplied by 10 to the minus 5 power, and the value of the decoding uncertainty index is 9 multiplied by 10 to the minus 5 power. The method can be used in conjunction with other methods or parametric and structural adaptation under conditions of a priori uncertainty. Thank you for attention.